Cambridge. Paul is an assistant teaching professor and research fellow at the University of Cambridge and has a degree from Queen's Belfast, an MPhil in nuclear energy from Cambridge and a PhD from Cambridge, and both do a ton of research on Monte Carlo methods. Oh, and while I remember Terrace at 5, we want to show them the local beer if anyone wants to go. Over to you, Valeria.
Amazing. Thank you. Yeah, thank you so much for the introduction. Ben already said everything, so I don't need to introduce myself or so much. Well, first of all, obviously, I would like to thank Ben for having us, for inviting us, organizing the day. It's amazing to see the campus, the department, and to meet everyone. So Paul and I are sharing the slot, so I'll go straight to the talk now, not wasting any time. Yeah, the title of my talk is Shortcutting Criticality Searches with the Zeta-eigenvalue equation. Okay, but before getting into the technical part, I would like to give you a brief introduction of our research group at Cambridge and SCOAN, which is our Monte Carlo code. Okay, so in Cambridge we have a nuclear energy research group. We're not big enough to have a whole nuclear department, so we sit in the engineering department. In our research group, we're about 20 people now. So we have 2 professors and 2 teaching professors that together supervise about 13 PhD students and 6 postdocs. The majority of our work, about half of the people in the group, work in radiation transport. That's our big focus. And in terms of in scale of popularity, the second biggest area for us is reactor design, followed by, I would say, nuclear data that we're trying to get more and more in. We have different sorts of fundings, mostly UK government and UK industry, together with some European projects, specifically reactor projects and some Cambridge scholarships for the students. And then we have a master's course on nuclear energy with about 20 students per year. Both Paul and I contribute to teaching the master, and we're hoping to grow the program, which is going very well this year. So as I mentioned, most of us back in Cambridge do radiation transport, in particular Monte Carlo and the random ray method, which is what Paul is going to talk about next. We do that thanks to our in-house code, SCOAN. SCOAN as a project has been going on for a few years now. Development started in 2017, I would say. We're a small developer core group, 2/3 people, but a lot of the students use it for their project as well. SCOAN is a unique project in the UK. It's the first high-performance open source code ever written in the UK, and the first high-performance,
radiation transport
code, Monte Carlo radiation transfer code ever written in the UK, and also the first high-performance radiation transfer code written in the UK in the past, 50 years. So yeah, we're very proud of it. The idea of the code is that the code was developed for developers, as it wants to be an easily modifiable code, such that if you're doing research in Monte Carlo methods, if you have an idea that you want to implement, the time it takes from implementation to, from idea to implementation to testing is as short as possible. Still, SCOAN has a quite extensive set of capabilities. Here we're showing off some impressive geometries that we can model and all of that. So it's a complete code. So both of, well, everything that I'm going to be presenting next, as well as for research, it's all done in SCOAN. Now on to the talk itself. As I mentioned, I will be talking about the zeta-eigenvalue equation, and then I'm going to show you some applications of this concept. Apologies for whoever was at MSc. There might be some repetition from my talk there, but also new stuff. So here you see, I hope you can see well, I didn't, I don't know if things are big enough on the screen. But here, I included a very compact version of the time-dependent neutron transport equation, where we have the time derivative of the flux, and then all the operators that have their usual meaning. So we have the leakage operator, the total collision term C, and then the fission and the scattering source. In a lot of practical application, you care about the steady state solution of this equation. And how this is normally tackled is we impose steady state by introducing an eigenvalue. So the most common one is obviously the K eigenvalue, in which case you impose criticality by adjusting the nu bar term of the fission source, so the number of neutrons that each fission reactor produces. by adjusting the number, you force your reactor to be stable. This is by far the most common eigenvalue used, but eigenvalue is, well, but you can, I mean, you can go wild and like define as many eigenvalues as you want. So like it is by far not the only eigenvalue definition used. For instance, like another quite popular or like useful one is the alpha eigenvalue equation, which I guess like it adds to the K eigenvalue equation because it can treat the time scales of the problem like accurately, whereas like K fails to do that. And these are the two common ones, but then there's like more obscure eigenvalues that probably no one ever uses, but they were defined at some point in time, like the collision C eigenvalue estimator, which scales fission as well as scattering as a source. The delta eigenvalue, which scales all the material densities in the system. So as part of this project, we defined a new eigenvalue, which we call zeta. So running out of Greek letters, got to the last one. So we're now working with the zeta eigenvalue equation that you see written here in its like most generic formulation. So in this case, the concept of zeta is that you can split every operator in your steady state Newton transport equation into two separate contributions, and then you scale one of these two contributions by zeta. In this equation, phi zeta is the fundamental eigenfunction or the solution of your equation for a given value of zeta. And then just to like define the useful things here, so like here, this equation gives you a way to map a value of zeta to a flux. You can also do the reverse. So you can also define a functional z that maps a flux back to the value of zeta. So in this case, this like functional zeta here, like in the most generic case again, is defined by integrating the top equation and like flipping everything so that you obtain zeta back from the equation. So this is how we define zeta, but what is it useful for? In the most generic form, it's like hard to see any physical meaning or like physical application. But if you go on and specialize, well, if you like write the equation in a like more specific way, you can use zeta to scale something of interest. For example, you can use zeta to scale, say, the material densities of a material or an isotope or a group of isotopes of your choice in your equation, in your system. And in this way, when you solve the zeta equation, what you get in practice is the scaling factor that that makes your system critical. So if your scaling density says like you will in practice obtain like the critical densities of whatever you specify. So this can be used instead of say a critical boron search or a critical xenon search, and so on. Otherwise, if you find a clever way to parameterize the geometry of your system, you can use again zeta for critical geometry searches, such as like critical control rod position search in a reactor. And I'm going to show you like examples of all of these next. So starting with the zeta density, which is how I guess zeta as a project originated. So here is again like slightly more specific version of the zeta equation, where again like all the collision, all the like reaction operators, so like everything except for leakage has been split into two contributions. And here I changed like notation slightly. So here I called M the material or isotope that you want to scale by zeta, and M bar or like negative M is like everything else in your system. And here you can see, just to like show this explicitly, so we're like scaling all the operators that that depend like linearly on your macroscopic cross sections. And when you scale your macroscopic cross section, given that your microscopic cross sections is fixed, in practice you're scaling an isotopic density. And here, like we can, just as before, like we can find like a more specific like shape of your functional that helps you to get a value of zeta tracing back from like a solution of your system. So once we solve this, again, like we get the zeta that makes our system critical. So next we went on to implement this equation in Monte Carlo, and here hopefully after with what comes next, like the numerics will be a bit clearer. So obviously we did this in Scone, as I said before. So we wanted to implement this new equation in Scone, and as I said, like zeta is an eigenvalue. However, an issue is that when you write this like zeta equation for densities as an eigenvalue equation, like in this formulation, the source of particles to be generated from one Monte Carlo iteration to the other would be like this one on the right-hand side of the equation. The problem is that according to your definition of M, that term can be net negative. And in Monte Carlo, there are some methods to treat like negative particles or negative waves, but they're a bit tricky and I mean, not necessarily always reliable, and like net sources, they're not necessarily well understood. So I decided to avoid trying to solve this. The advantage of solving this would be that this could be solved by the conventional power iteration Monte Carlo algorithm, but I chose to go another way. So I chose to write my equation maintaining the same structure, let's say, of the k eigenvalue equation. So like with the term like written in the same like order, like left and right hand side. This way I cannot use power iteration anymore, which is a disadvantage because power iteration has like very clear, well understood convergence properties. However, the advantage when doing this is that like all of my terms are positive. So I end up having to solve this with a more generic fixed point iteration numerical algorithm. So, however, like obviously the advantage is that we retain positivity, and also that in a Monte Carlo code that has already implemented the k eigenvalue equation, implementing zeta now requires very minimal modifications, because like the particle tracking, the treatment of collision physics, the generation of the fission source from one cycle to the other, it all stays the same. So that makes implementation super easy. So how the implementation actually works, again, this is identical to the classical like eigenvalue equation, but k is fixed. So k, oh, sorry, I forgot something, that here like I added a term lambda in this equation. Lambda is 1 over k, and in this case, lambda is a user-defined parameter. So you can fix whichever value of k effective you want to target. So you're still like scaling the fission source, but with something fixed. So if you say I want to obtain a k of like 0.95 for some criticality safety applications, you can do that without any issue. So here like you can, yeah, so that's not exactly accurate. You can still like scale the fission source, but like by a constant defined by the user. So not by something that you calculate every cycle. You still need to start with an initial guess for your fission source and for your zeta. Then every time in your code, you need to look up a cross-section for the material or isotope M. You scale its atomic density by the current value of zeta. Every cycle, during the cycle, you use your like definition of the Z functional fed with the flux to calculate the value of zeta for the next cycle, so the zeta update. You still use inactive and active cycles. So during the inactive cycles, you converge your zeta as well as your fission source, and then you collect statistics during the active cycles. Yeah, you can still calculate k effective, but you don't use it in the calculation at any point. A caveat of this algorithm and of the method in general is that you need to, well, in order to obtain like a physical value of zeta, which in this case means a positive value of zeta, you need to ask for something sensible. For instance, if you are performing a critical, like, I don't know, gadolinium search in a problem that is subcritical without any gadolinium, then your zeta is going to be negative. It's going to tell you you need negative gadolinium to become critical, which obviously doesn't make sense. So you need to pose your problem in a physically sensible way. So a few numerical examples with these, like the toolkit for zeta density searches is complete. The first example that I tried was a critical plutonium-9 search in POPSI. So POPSI is a criticality benchmark made of a plutonium sphere surrounded by a uranium reflector. By definition, this problem was already like approximately critical, so I made it off critical to then like retrieve criticality. So what I did is I made up a density of plutonium-9, which gave me a K effective of about like 0.88. And then like I perform my zeta calculation and I obtain the critical density that gives me essentially like K equal 1. So yeah, this works very well. One thing that I noticed is that while like each Monte Carlo iteration took about the same time for like K or for zeta calculations, I needed slightly more cycles to get the statistics down in zeta. I think this is because of how the estimators for K and for zeta are defined, or like the difference between the two. In K, all of my integrals, they're like over the whole domain. K is like a proper like integral parameter, whereas in zeta, we're integrating certain terms in like smaller parts of the domain. So whatever contains material M and whatever doesn't contain material M. So these like local integrals, they make my estimator a bit noisier. So I will need more stat to converge zeta. But yeah, otherwise, everything worked as expected. I had like several like numerical tests to show, but because of lack of time, I will go from like the simple one to the full scale reactor one. So I performed like a few different ones, some gadolinium searches in a PWR, some water density searches again in a PWR. Here, this is an example of a boron search where I'm scaling the density of boron 10 and boron 11 in 3D in a 3D model of beavers. I didn't include the K effective with the original concentration. I don't remember what it was honestly, but here you see like the convergence properties of. Sorry, this is like the text is very small, but you see the convergence properties of the zeta calculation essentially. So here you see. So in this plot, you see like the convergence of the eigenvalue as a function of the inactive cycles, and here the Shannon entropy, which is a measure of how the fission source converges. So in terms of the eigenvalues, here you can see the blue line is the convergence of zeta, which converges to a fixed point or around this fixed point. The red line is the convergence of K effective calculated by the zeta calculation, which converges to 1. And the yellow line is the convergence of K effective in a K eigenvalue calculation with the critical density of zeta, which also like converges to 1. And the fission sources in a zeta calculation and in a K calculation, they converge at about the same rate. There's another like caveat to keep in mind, or something to keep in mind. And this is that the convergence property of zeta, they're very different from the convergence property of K. You don't see it in this problem. And like this problem is relatively neat because like the two problems, like K and zeta, converge basically like at the same speed. But this is absolutely like not generally the case. One thing to, one important thing to keep in mind is that in K eigenvalue calculations, your K effective is K's the fission source uniformly. So it doesn't modify the shape of your fission source. So the convergence properties of K effective and of your fission source, they're independent from each other. And we know them reasonably well. In zeta, because you're scaling something localized, you're actually affecting the shape of your fission source. So the convergence, the speed of convergence of the zeta calculation will be equal to the speed of the slowest convergence between zeta and your fission source, because they need to be both converged for the problem to be converged. So in beavers, the convergence bottleneck was the Shannon entropy, which is why, which is the same as in K eigenvalue calculations, and this is why the two calculations converge at the same rate. In other problems, the convergence bottleneck might be zeta instead of the fission source, in which case the convergence of the problem as a whole will be slower than in the case of K. So we're doing a lot of work on studying and analyzing these problems, but I will not go in any detail here because there's not much time, and there's the second chunk of presentation to go through. So the second part of the presentation is to apply the same methodology, or like a slightly modified methodology, but this time to geometrical searches. So before going into zeta, and this is like a bit of a slightly a change of topic, but before going into zeta, we need to address how we can perform geometrical perturbations in Monte Carlo. And this is all very new stuff, or rather, like this is stuff that was like theorized or like written up in the I don't know, like 50s or 60s by like Russian scientists, and then like our colleague Nikolai Kowalski, he fished it up, understood it, implemented, and this is like a very recent Monte Carlo development. Amazing work, sadly it's not mine, it's Nikolai's, but I've been using it. But essentially, like his work, like what he found out is that you can apply virtually like any geometry perturbation in Monte Carlo if you do it by perturbing the coordinate system rather than perturbing the geometry itself. So I think this picture is quite neat. So like in the first picture, like you see what's your geometry, like CSG definition in Monte Carlo, say in your Cartesian coordinate system. Say that you want to, you would like to deform this geometry to be able to simulate this like perturbed, this like deformed system. Mikolar, like the theory essentially says that if you perturb your coordinate system instead, your deformed geometry in the deformed coordinate system looks exactly like your original geometry in a Cartesian coordinate system. So you can simulate, you can model this geometry by modeling this geometry if during particle tracking you essentially perform a coordinate perturbation, like a change of variable, basically, which is again like very, very easy to implement because it all happens during the particle tracking bit of Monte Carlo. And how you do it depends on which kind of perturbation you want to implement. For instance, if you want to implement a uniform perturbation where you scale the whole model geometry, you do it by perturbing the omega, so like the direction vector of your particle. If you want to apply a non-uniform perturbation where you only perturb part of your geometry, then you normally do it by, with like a more like perturbation-based approach, by like applying a perturbation field F to your like starting to the position itself of the particle. This is all I'm gonna say about perturbations in Monte Carlo. So back to zeta. I'm gonna show the application of zeta only in the case of uniform perturbations because it's slightly easier and there's no time to cover everything, sadly. So in this case, I mentioned that we're applying the perturbation to the omega direction field, direction vector of the particle. So in the case of zeta, we're like perturbing our leakage operator. Here again, like I also saw from like 1 over zeta to zeta because it was more convenient, but it is the same, it's just about definitions. But essentially we're like, perturbing our leakage operator with this like dot product with like a vector zeta, where like when you expand this, like it becomes like this, it like breaks down into 3 components where like each component of zeta multiplies the respective component of the direction. However, like how zeta works, like we only want to have like one parameter. We don't want this like X, Y, and Z. So in practice, the type of perturbations that we can apply are limited. We only want 1 zeta parameters, but we can do, for instance, like isotropic deformations where like the whole model like expands identically in every direction, axial, radial, or like any combination, as long as we only have 1 parameter. In terms of the zeta functional for the update to calculate zeta during our Monte Carlo, writing an update like we did previously for the density, so like based on the actual like balance equation for the generic coordinate perturbation case is, I think it's possible, or at least like very, very hard. Luckily, we realized that the update doesn't have to follow the same rules. Like any update would work as long as certain like simple rules are respected. For instance, this is like a non-linear like iteration method. So the only conditions that we need to satisfy are that your zeta functional at the fixed point, when evaluated, returns the fixed point, zeta. So like once you reach the solution, you stay there. And then the like zeta drives your like zeta variable to the fixed point. And you need this condition on the slope of zeta around some interval of the fixed point to be valid. So like as long as you satisfy these two conditions, you will converge to your zeta. So we had, well, I've been like playing around with two alternative of the updates. One, like, yeah, using like leveraging essentially like the balance equation, which needs to be satisfied at criticality, which means that this ratio at the fixed point needs to be 1, fair. And the second one using this like relation on K effective, which again like has to be 1. And like which one to use of the K effective depends on the sign of the sensitivity of zeta to K to partially satisfy this like condition. However, like satisfying, well, like knowing if this condition here is satisfied a priori with either update is impossible. So like there's a bit of like trial and error. If you try a new problem, you need to like try different updates and you need to hope that it's stable, essentially. Like stability of convergence is slightly an issue. But yeah, with these, like the Monte Carlo implementation of the method for geometry is like very similar to that of density. So I'm not gonna go through it again, and I'm just gonna show you some results. The first one was again like the simplest case, which is a uniform isotropic perturbation of a sphere. In particular, I tried 4 different spheres made of different like fissile nuclides, all with a starting radius of 10 centimeters. And yeah, by applying zeta, I can find the critical radius that gives me a critical system, essentially, all very quick and simple. And the neat thing is that, contrarily to perturbation-based methods, you don't need to be close to the solution to be fully accurate. So here for the uranium-235 case, I did a zeta calculation for like different starting densities going from 10 to the minus 1 to 10 to the 3 centimeters. And I always converge like exactly to the same critical radius. So this is, as long as like convergence as long as stability of convergence is not an issue, the method is like fully accurate. Once again, I go from the like simplest case to the most complex one for, because I'm already out of time, I think. So next I did a proper like full scale reactor calculation. In this case, a control rod bank position search. So this is a cut of the LDR50 model. It's a 7x7 PWR model, about like 1 meter tall, Finnish reactor startup, essentially. So yeah, like a small PWR. And I modified the position of one of the banks of control rods. I try to highlight the control rods that I've been perturbing with bright colors, but I'm not sure you can see them. But essentially, it's like these two, these two like in these assemblies. So the original position of my control rods was like I had like water at the bottom of the core. Starting from like 10 centimeters from the bottom of the active core, I had like 60 centimeters of inconel, which are like fixed lengths. And then like from there to the top of the core, boron carbide. So what I want to do is I want to perturb like the length of the water, keep the length of the inconel fixed, and counter scale the length of the boron carbide to compensate for the perturbation in the water. So we did that. This was like slightly like lengthy calculation, but like it converged again to the critical value, which was like moving up these the end of the control rod from 10 to about 22 or 23 centimeters. In this case, I repeated this run like multiple times. Each time, like here, you can see like the zeta values and the error bars of each prediction are like within this like little square. So clearly, like because the update that I've been using is like heavily correlated, the uncertainties in my zeta predictions are not at all reliable. But perturbing like independent runs, I could calculate like the mean zeta, and these are like 2 standard deviations out of zeta. And then I evaluated. I performed like a K criticality calculation using the zeta values like 2 deviation like above and below the mean. And both of them were critical within uncertainty. So essentially any mean value of zeta produced came in like a critical problem. So that's it for today. Sorry, I went a bit long, Paul. You'll have to speak very quickly. But future work on zeta will be, I think I insisted a lot on convergence because like that's the trickiest part of this kind of work. But studying convergence properties, both in terms of convergence rate and stability of convergence. And also trying to use zeta to calculate sensitivities. Essentially, what we have here is, especially during the active cycles after convergence, each cycle we're producing a K effective given a certain value of zeta, which is kind of a total Monte Carlo like run in a way. So maybe we can use like these values during the active cycles to calculate sensitivities of K to zeta, which means of K to densities or geometry. But this is like this is a very new idea. I'm hoping like to submit it for Pfizer if it's successful, but we'll see. Yeah, that's it. Thank you. I don't know if there's time for questions. Maybe Paul, you want to go first?
I don't know. What do you think? Should we bunch questions together, or?
I would suggest do yours and then bunch for questions, because
Okay.
otherwise there's a risk that we'll end up at 1 o'clock.
Yeah.
Sure.
Okay.
Thank you very much. I would also like to echo Valeria's sentiments. Like, thank you for having us. Thank you, Ben. I'm going to be talking about random array for shielding problems, or in particular, I guess with a view to fusion problems. I'm not sure how many of you will have heard bits of this from Professor Shuwai, but hopefully there'll be some new things or some interesting things. So, yes, I would also like to thank John Tram, who some of you may know, and my PhD student Rufus Neem. Many of these results I'm going to present were produced working with them. So thankfully, Ben mostly covered the about me, so I'll not go through the bio bits, but I guess I'll say my research interests are either in sort of algorithms that we use in nuclear engineering, various aspects of nuclear engineering, how they behave. You know, can we think through an algorithm before we implement it? Is an algorithm an idea, a bad idea a priori before we go through the implementation step? And can we say whether it'll converge or not? Things like this, or how efficient they'll be. That's one side, and also ideally using these algorithms to tackle problems that we couldn't easily tackle before. And hopefully, in some sense, this talk has a little bit of both of those. So, the random array method. I'm not sure how many of you are familiar with this, but I'll go relatively quickly trying to cover the background. So we've got here the transport equation, where we've got leakage, collision term, and a source, a generic source of some sort, which varies in space, and or flux, solution which we're after, varies in space, angle, and we've already discretized it in energy into groups. How we often, or how in nuclear engineering, traditionally we've often approached this is by considering the characteristics formulation of this transport equation. We say, instead of dealing with this nasty omega dot nabla, what if we just considered the transport equation along a straight line through the problem, give some starting position and some starting direction. You do that, and you do the chain rule, and you're able to say, let's consider our angular flux at some point S ahead down this path. So now we're solving for a flux at some point in the distance. And this equation can be solved very easily if you make a few assumptions, like if you say your source is flat or constant in space, and I'm sure a few other approximations I'm forgetting, but I think that's the main one. You're able to solve this by an integrating factor solution and obtain this equation where you have to know some initial angular flux at the point you're starting at. Yeah, before I show that, we're only doing this for a single track, but if you choose enough starting positions and starting directions and cover your problem of interest sufficiently well, you should be able to get your flux solution that you care about. You don't care about the angular flux. In the end, you care about usually the scalar flux or the reaction rates across your problem. So where the method of characteristics starts is given some geometry, here a standard pin cell. If you draw lots and lots of tracks and solve this equation along these tracks, like sort of relatively coarse layout actually for these tracks in the standard method of characteristics is shown here, then you should solve your transport equation. And this is done in industrial reactor physics very frequently. And this is where we start from. So this track laydown, this quadrature, is quite optimized for several reasons, but it should cover the phase space relatively well, hits many of the points, many different angles, many different positions, and that's good. That's what we want. Where random ray begins is to say, what if instead of having this really well and intelligently chosen quadrature, we instead have a quadrature where we don't focus on where we place these tracks, we just scatter them randomly with different starting positions and starting directions. And if you were to just do this and run with that, it would be a really bad idea. You would get a much worse result than what you had before. The intelligent bit of random ray is to say, what if we have this random quadrature, but every single iteration we vary it, we let it change. What this buys you is that it turns a biased quadrature or a biased integration of your phase space into a Monte Carlo sampling of this integration of your phase space. So this is all sorts of benefits, which I don't really have time to go into. We can elaborate during questions if you like. But this buys you things like it eliminates angular discretization. You might maybe, if you don't have enough rays, you might be undersampling your angle, but if you have a relatively coarse number of rays, you should essentially wipe out any angular discretization errors. It also allows you to have a very coarse quadrature on a given iteration, as opposed to previously we had to have actually a very fine quadrature to get a good answer. On a given iteration, you're going to have a very coarse quadrature, but then the points that you miss on this iteration, you might hit to the next one, and so you'll cover that bit of phase space eventually. So this means that given that most of our algorithms that we're interested in are iterative, this allows you to go through a given iteration much faster than you would by this traditional deterministic method. So it buys you potentially quite a lot of speed solving these problems. So the problem is that because it's now a Monte Carlo integration, we have sort of the familiar problem that we have with well, Monte Carlo in neutronics or Monte Carlo for k eigenvalue calculations. You spend some time during inactive or discard cycles where you're just converging your solution, and then once you've converged your flux shape, you then have to start scoring the Monte Carlo integrals. You're not scoring it beforehand because otherwise it would be biased. Once you've converged, then you start scoring to get rid of that 1 over square root n uncertainty, or to minimize that uncertainty, your results. So this is a cost that you wouldn't have in a deterministic counterpart where you would sort of converge to there and then stop. You've got your answer. So this is where random ray is, and so far in deterministic method, or sorry, in sort of reactor analysis, it's shown quite a lot of promise. It's also got a lot of promise in terms of parallelization and things like this. However, I guess where this presentation starts from random ray is to say, once we applied the method characteristics to fusion problems or shielding problems, and maybe the question is why, or rather, why not do other things? What does this method buy you? So in fusion in particular, essentially, really the only method in town to date has been Monte Carlo. Everyone uses Monte Carlo most seriously for fusion calculations. Why is that not good enough? Or why can we do better? So one problem in fusion calculations is maybe not for, say, estimating your tritium breeding ratio, but for things like shielding or getting results at the end of ports, for diagnostics and things like this. Monte Carlo struggles because the problem is you've got to force these particles to go through 10 to the whatever, 10 to several orders of magnitude of neutron attenuation, which means that if you did it naively, you'd have to simulate orders of magnitude numbers of neutrons, which would be very slow. So you've got to do things like variant instruction, and there are very clever techniques in variant instruction these days, but they are still slow. It's still quite lengthy, and they still have challenges with parallelization and things. So that is a bit painful. Furthermore, so I should say on this variance reduction aspect, we've seen random array, which you might suspect this stochastic method might also have challenges with variances like standard Monte Carlo. In reactor analysis, you can get a little flavor of just how much of a variance challenge it has in fission reactor analysis, that is. So some work I've done with John, we looked at this problem C5G7, which is a little 4-assembly reactor. And we simulated it with both Monte Carlo and random array, running it for the same amount of computational time, or sorry, same amount of clock time rather, on the same node. And what we see when we look at the uncertainty distribution with Monte Carlo here is that, as you would sort of expect with Monte Carlo, in the core, your uncertainties are very low. That's where neutrons live, and most of them die. So you get a lot of scores there. Whereas at the edge of the core, this isn't a very big core. You know, this is a distance of 14 centimeters or 17 centimeters or something like that. At the edge of the core, you've got sort of 10% uncertainty, which is relatively quite a lot, more than we'd usually tolerate for a good result. Whereas with random array, essentially your uncertainty is uniformly flattened, quite low in the order of 10 to the minus 3 to 10 to the minus 4. This is because these rays that we sample, we don't sample the rays in the fuel, which you have to do for neutrons. The rays are sampled uniformly across the system, so you get this good coverage. Another thing, so Monte Carlo also applies you accuracy, continuous energy, which is really great to have. You might want that, again, for your TBR, where cross-sections matter quite a lot. But maybe for shielding, where we care about orders of magnitude, you don't really need that, or for getting scores in diagnostic ports, you don't need that so much. So maybe you can afford to have this multi-group discretization error. But yeah, that's up for debate. I'm happy to be challenged on that. On the other hand, why not deterministic? Why do other deterministic methods not see a whole lot of action in fusion? So one is what I alluded to earlier, this angular discretization error. When you have a strong source of neutrons, here shown at this point in the middle, which is in an absorbing medium, what you often see, and what many people in deterministic, especially in shielding problems in particular, not so much in reactors, fission reactors, suffer from is what's called the ray effect. Basically, you get a very visible imprint of your angular quadrature. Here, I think, you know, here they've chosen 8 different angles to cover in 2D space. Maybe it's an S8 quadrature or something like that. But they chose this particular quadrature, and you can see the actual directions that they've chosen here, which is obviously unphysical. If you've got an isotropic source, then your solution around it should be isotropic as well. So the only way to overcome that with deterministic normally is to just do more rays. Well, there's some other tricks as well, but it's hard. Basically, you've got to put in more effort and care. With random array, you just get this angular coverage naturally. You're not discretizing an angle, so you avoid that. You avoid all of these challenges. Another thing which is less talked about, but very relevant, I think, for fusion applications, is that many approaches in deterministic transport require, well, all approaches require discretizing up space as opposed to Monte Carlo. Many of them have quite severe restrictions on how this discretization of space looks, as in they can't necessarily handle curves very well, which is an inconvenient thing not to be able to handle. To capture these curves well, you might have to mesh things up quite finely. So here is a fuel pin, and here's what someone, I'm not saying that this is necessarily the state of the art in deterministic, I should say, but here's what someone with their SN code had to mesh up to get the right answer. Whereas with the method of characteristics, because you're doing this tracking across, well, you're following neutrons across these tracks that you lay down on the geometry. These tracks don't care whether the mesh element is circular, tetrahedral, or hexahedral, or whatever. You just do the ray tracing and it'll tell you the answer. So you can keep these curves. It's maybe an interesting question, why was this not applied to shielding problems in the past. Why was the method of characteristics not applied to shielding problems in the past, given that it has this advantage of these, in principle, exact geometries? That is because in the past, with this this quadrature that we saw earlier, this very fine quadrature, it was actually a very big memory footprint that people couldn't afford. However, with random array, I think I didn't say, sort of implicit, is that when you're retracing your arrays every single iteration, you're not storing any of this track information. Once upon a time, that was a really big deal. Once upon a time, if you look at most of the modern textbooks, actually, which say about the method of characteristics, they will say the big computational cost is doing the ray tracing. That was maybe true in 2010. It's not true anymore. So now you don't need to store these things to get a fast, accurate solution. So we can preserve geometry and we can avoid this angular discretization effect. So this all, as far as I had felt, was very natural for applying to fusion. However, there were some really interesting problems which we did not expect. One of them being negative fluxes turning up. So those of you who are into deterministic transport, this may come as a surprise because the method of characteristics should have this property of guaranteeing positivity in your fluxes. In the random array method, you don't have that property for sort of interesting reasons. So how we define our scalar flux in mesh element I, forgetting about groups for now, is it's the integral of the angular flux over that mesh element in space and an angle. In the method of characteristics, how you tend to deal with this, because it's actually just faster, cheaper, is you tend to split out this bit of source here and deal with it separately, and then you've got this angular flux term that you spend all your sort of iterations figuring out. Yeah. So this is a slightly weird approach, but it just happens that this is faster. It spares you some flops, essentially. So we can evaluate some of these integrals. We could say this volume at the bottom, that turn into VI, the volume of your mesh, and we can get rid of that angular integral over there and say that our source is isotropic for now. The problem arises because those two terms that we just split out, they should cancel each other if you did everything correctly. Like those two things, you should just be able to add back together and everything should work out fine. Also, these two volume integrals should be the same, but actually they're not. Usually what we do is we cancel this volume integral on the top and on the bottom out if we assume that this source is constant in that mesh element. This volume cancels that, fine. The problem is that this volume, how we tend to evaluate it is actually by how much of our given mesh the rays cover, or how many rather tracks cross this given mesh. The more tracks that cross that mesh, the more volume that mesh should have, or they should be proportional in some sense. However, on a given iteration, it'll vary stochastically. So these two volumes aren't necessarily equal. So there could be a scenario which is very plausible and indeed physical, which is that if this source happens to be very large and this cross-section here is very small, as you might find in a plasma, for example, then the source term can greatly dominate this flux term, right? As well as this, if stochastically this volume integral happens to be a little bit bigger than this volume, then these guys don't cancel and you're left with a negative scalar flux, which is obviously not physical. There is a way of ensuring this positivity, and that is by a clever choice of what these VIs are. You don't have to actually choose the physical volume. It's weird. There is some choice in what you decide the volume of this mesh element is. You could say that this mesh element's volume is just the volume that the tracks that traversed it cover. If you do that, everything actually cancels very neatly. Problem is that gets you a ratio estimator, which those of you in Monte Carlo may be familiar with this. But basically, the short statement of this is that the average of a ratio is not equal in expectation to the ratio of two averages. There's like a bias there. If you have a huge number of samples, then that bias will go to zero, but there is a bias there, which is very unfortunate. And we've got to that's sort of the choice that we're dealt with here. The other problem related to this, which is also very interesting, is problems in the thin streaming limit. People in transport often care about the limits of the transport equation, especially with respect to discretizations. Mostly they spend their time, especially in weapons applications, actually talking about the thick diffusion limit. If you've got a really thick mesh, does your transport discretization approach a diffusion equation? If it doesn't, that's a big problem. So people spent careers figuring this out. Much less often do you hear about the thin streaming limit, where if you've got a very thin mesh with a very small cross section, does your transport discretization reduce to everything just streams across it? So the thin streaming limit applied to the transport equation looks sort of like this. Your collision, any term with a cross section disappears. Basically, your flux or your leakage results from your source. And in characteristic world, you can write it as this. The problem that we have with random ray and standard MOC is that if you happen to have no rays crossing a mesh from the previous slide, just to remind you, if you have no rays crossing a mesh, this volume integral goes to 0, right? Just left for this guy. Oh, whoops, sorry, wrong way. So that, just leaving you with that guy gives you this. That's what your flux is in your mesh. However, in the thin streaming limit, that's not actually what you get. In the thin streaming limit, everything disappears, everything leaves. So basically, the problem is that in a plasma, so if you happen to miss that mesh which contains a plasma, what you're saying by default is that we're putting all of the flux, all of the sources staying here, which is actually unphysical. Everything should stream away. This is a big bias, or it can be a very big bias. So to sort of demonstrate this problem, Valeria said earlier about how our geometric capabilities in SCOAN are really good. There are still some limits. This is a sort of little toy fusion problem. OpenMC can do much better. Here is a plasma surrounded by mostly near void, not completely void, but near void, which is transparent, and then surrounded by some absorber. Very simple, one group problem. And it's reflective boundaries here and here to the bottom. So that's an octant of our plasma problem. And here are the relative sizes, very small. We scale the density of our plasma because that's sort of what everything depends on, that we were just saying. Our negative fluxes should appear more when we've got a strong source in a material which doesn't have any collisions. Likewise, our thin streaming limit should disappear as our source becomes more optically thick. And basically what we see is we can compute the errors with respect to a Monte Carlo reference, and we can estimate our fluxes in, we estimate the integral fluxes in each of these regions. And what we find is that our error in our source is 1000% when we have a very low density source. Even if it's nearly void, as in the void region, it's still, out by quite a lot, uncomfortably a lot. As it happens here, the errors in our void region and our absorber region aren't so severe, but there are some circumstances where they can be quite nasty, actually. So then it comes to fixing this problem if we want to apply random ray to diffusion. And there are a few approaches. Well, first is sort of the business as usual case, not a fix, like just do what we did. We'll compare that. So that is use our exact or near exact best estimate volume estimates for every single mesh. And we treat misses as we usually do. We just deposit all the source there. The other is applying some combination of these fixes. We could use our as traced volume, or as we call it, the naive volume estimate that gives you this ratio estimator bias. And we could apply, in principle, the thin streaming mistreatment, which we don't set to 0 actually, because setting it to 0 is correct in the thin streaming limit, but maybe you have an inhomogeneous source which isn't entirely thin, so you might want something intermediate to that, which is actually well covered by just setting the flux locally to what was there in the previous iteration. And then you can do one thing that's just a little touch more clever. I'm sure there are many things you could do which are quite a lot more clever, but you could apply this naive volume estimator, which we don't want to apply only in regions with an inhomogeneous source, and likewise apply this thin streaming treatment only in those regions as well. So you don't suffer the errors that they might accrue otherwise. And how does this look at that same little fusion problem? We also do this, I should add, varying the density of our tracks, because the more misses you have, obviously, the worse this gets. Or indeed, the larger the uncertainty in that stochastic volume estimate, the worse this should get. And what we find is that as we change our miss rate, as we coarsen our quadrature, the errors become quite severe in most of the other treatments. If you are missing 10% of your meshes, then you can expect orders of magnitude errors in your sources, as opposed to if you have this treatment we just proposed, or these fixes that we just proposed, you will nail sort of sub 1% errors, which is very nice. That's what we're hoping for. Again, this is mainly in the source region you see most of these benefits. However, if you're not careful, you can also get some quite significant errors, or errors that you wouldn't really want to tolerate in the other regions too. And I should say, typically, or in the past, with random ray, the sort of advice had been, you should always try and hit about 99.9% of meshes. Actually, with these treatments, you can hit only 90% of your meshes. And what this means is that you can speed up your calculation quite a lot. You can have a much coarser quadrature, so you get a lot more benefit. So I see I've got 2 minutes. Ben, what do you think I should do?
I guess the question is I would probably suggest wrap up so we can ask you some questions,
okay.
If that's okay.
Sure. Yeah. I'll give a very brief flavor of the 2 more slides I have.
Okay, yeah.
Very, very brief, just so people can ask questions if they're interested. So another thing we would like to do is we'd like to coarsen our meshes a lot more. In fission reactor analysis, usually you've got pretty fine meshes because neutron mean free paths are small. And you've got changes in composition over relatively short distances due to changes in coolant density or changes in fuel composition. Actually, in fusion, you don't have that so much. I mean, you might have very fine structures, but the change in the cross-section forcing a discretization doesn't need to be that fine. So this means that you can have extremely coarse meshes if you're clever. So basically, we can apply some tricks that people had done in fission applications to allow you to coarsen your meshes out. We demonstrate them here in fission, but mainly this is just applying them to random ray, and it shows that they work pretty well. So on a fine mesh, you get pretty good error, and coarse mesh using these tricks, you also get a very good error. The main thing to focus on is that you can speed calculations up quite a bit with this coarse mesh approach. And this should have a much more significant benefit in fusion, where you should just be able to coarsen more. Most of these applications, in fact, this application itself is relatively academic because you have this big reflector region, which isn't necessarily representative of most fission problems. Also, this happens to benefit very nicely on GPUs because with these linear sources, the trade-off that you have is in coarsening these meshes is that you spend a lot more flops on handling this linearity of your source that you're saying now exists. These extra flops fit really well on a GPU. So you can solve this problem you can solve this linear source problem and port it over to a GPU, which one of my students, Rufus, did on with OpenMC, actually their OpenMC random array implementation. And I guess the take-home point is that with linear sources, going from CPU to GPU gets you a 10 times speed up, as opposed to with flat sources where you get only a 5 times speed up. And going from flat source to linear source on a GPU also gives you a 10 times speed up, whereas it gives you only a 6 times speed up on a CPU. So they're big speed ups to be gained. And again, this is all in a fission problem where he was very careful to treat flat source and linear sources equally, or not be too biased towards one or the other. So yeah, I think there's some advantages to be gained there. So my summary is mainly that random array, I think, is sort of the first kind of deterministic method, which I think has shown sort of significant promise on fusion problems. And I think there's a ways yet to see where it goes. There are other tools in the deterministic toolbox that we can apply to these. Like we've already applied linear sources. You can do things like, I don't know, computing adjoints for sensitivities, which Actually, no one really does it in deterministic. There's a lot of maths there for it, but it's very impractical. I think with one or two like clever bits, you can now apply them to you can apply them with a lot less cost. And Rufus has worked on that yet, but I don't have that to present today. And I think yeah, for weight windows, as those of you familiar with thermodynamics will know, random array is quite established, I think, at this stage, or is getting there. I think it could be a design scoping tool for fusion applications. People in Commonwealth Fusion, they use Attila for some of their design scoping applications, but it seems to have a lot of problems, is my understanding. I think there's a lot of money spent on getting perfect quadratures to hit particular experimental ports. With random array, I don't think you need that. There are still things to be done with improving cross sections and handling anisotropy, but yeah, I think it's a very conceivable path. I think there's some interesting research to be done there. If we want to treat fusion in the same way as with fission, where we can do many design iterations very quickly, we need probably something that is a bit faster than Monte Carlo. And yeah, this could be it. So yeah, thank you for listening. Sorry for running over time a bit.
If anyone needs to dash, feel free to leave. But if people want, we can keep some questions going and overrun a bit if those of you wish to ask questions. Any questions?
I have a question. This one's the first presentation. So, like, it seems pretty new, but is there general guidance on when zeta will outperform a traditional Monte Carlo AI value? Oh yeah, sorry, I'll say it again. So zeta seems like still pretty new, right?
Mm-hmm.
But do you have any like general guidance on when you think it will outperform a traditional K eigenvalue search for K effective, or is it very problem dependent?
Yeah, so I think it's very problem dependent. I didn't show them, but I did some comparison between like finding criticality with zeta or with like iterative like K searches, trying to make the searches like as smart and fast as I could. I did that for the density, and in all of those problems, like zeta was like much faster. Even in problems where like maybe to converge like zeta, it took me like longer than it takes me like to converge K. See like like you would need like several K iterations, so like that pays off. The geometry work is much newer. In the geometry, I think there's like, well, as of now, like I still haven't optimized anything for speed. But in the geometry case, like there's much overhead in doing zeta in some problems because the perturbation method only works with delta tracking, whereas certain problems like the LDR50 problem, for example, it's much, much faster if you simulate that with a combination of like surface and delta tracking. So yeah, doing zeta like, well, convergence took longer, plus I had to use delta tracking, plus the geometry perturbation adds a bit of overhead. So overall, like the zeta calculation was like much longer than a K calculation. I don't know how long now. But still, like it depends on how many K iterations you would need to get there and which precision on K you want. Because here, like you converge to like exactly the like, I mean, within uncertainty to like the critical position or density.
In zeta, you pick K.
Yeah, exactly. In zeta, like so I think it's competitive, but like definitely the geometry method, it has to be optimized a bit.
Awesome, thank you.
Can you put more than one thing at once in the zeta method?
Yes, but with the same factor.
Right, okay.
Yeah.
You can't like preserve both. Say if you got water changing both density and actual Doppler temperature, could you put both of them into the same hood?
So wait, if you perturb.
Yeah, that sort of thing, right? If you had, suppose you had some concept of, well, maybe everything was changing temperature, but some things were expanding more than others. Can you do that?
If you can relate them, like I think convergence, if you had like two scaling factors, I think convergence would be a nightmare.
But if you had a closed form way of describing how those factors depended on each other.
Yeah, for example, like I just had a student doing always like density related, but like finding a critical enrichment where like you scale something up and you scale something down.
Yeah.
As long as you just have a factor. So like if you have that closed form, yes. Convergence like two values, zeta1 and zeta2, say, I don't want to get near that. I think that would be awful. Yeah.
I guess it wouldn't be a closed form of it. You'd have like a line of solutions, so like zeta1's this and zeta2's that, and yeah.
Yeah. Yeah, I mean, convergence is the biggest issue, honestly. I've shown that successful cases.
Yeah.
Other questions?
Oh, thanks so much for the presentation. My question is for Bob. This is like really low hanging fruit, but like what sort of cross-section generation routes actually do like have been thought of for the random array?
So in
Method?
OpenMC, there is an approach, certainly for the weight windows. I think there's a choice of 3, if I recall, which vary a little bit, and there's things like handle, but a source in a homogeneous region, generate cross sections for that, or maybe Patrick knows better. I'm not sure.
Yeah, there's a few. Like you can do it in an infinite media and generate multi-group cross sections that way, or you can do, there's like a stochastic slab method. They're all really rudimentary in summary, and there's a lot of room to explore better cross section generation routines.
Yeah, actually, yeah, we did talk about
We
that,
talked a little bit about that potentially in the future. It's not clear, like, I don't know, it's a hard problem because it can be really geometry dependent. And the anisotropy that Paul mentioned too is a big one to look at as well. So.
Is random array implemented in Stone as well?
Yes. Yeah, maybe I should have said that.
I guess seems like a lot of the issues with random array are still just not fully sampling the phase space. Would it be possible to do bias sampling of some kind with your?
I think in principle it is like yeah, I don't think there's any reason why not. It like adds some bookkeeping because things like different rays have to have different weights, and it might also, or it will also affect how you're estimating the volumes of different regions. But I think with enough effort in the bookkeeping, it's very conceivable.
It would be more effort to bias the rays than it would to just sample them uniformly.
That's the question. That's the question. Yeah, I mean, if so, I think maybe if there was a good application where the variance reduction was necessary. I mean, just because at least with any random array calculation I've done, I've never seen like a huge variance. There is like some variance, which is due to, I think, essentially flux gradients actually, or physical flux gradients. But there's not an order of magnitude thing where like there's a clear benefit that applies you, but there might be a case. I can imagine maybe things like, so random array is like inherently 3D, but there could be a case where if I want to simulate a 2D problem, you could bias it in such a way to like cover the polar angles appropriately. That might not even be too like, might not even be too nasty with respect to how it affects weights and volume estimates, but that's one thing you could do maybe with bias.
Any more questions?
I had a curiosity about I think it's the what about fusion slide where you showed like the comparisons. If you could go back to the slide.
Yeah.
Like it was when we were showing the relative errors.
Yes.
Yeah, this one. So in the random array relative error picture, there seems to be some kind of pattern manifesting from the geometry. Do you have an explanation as to why that happens?
Yeah, this is sort of what I was alluding to a moment ago. I think it actually does depend on flux gradients is my best sort of physical intuition for it, especially because, so when you think about it, most of the uncertainty, the largest uncertainty is over here. That's the corner of your geometry, which this is a vacuum boundary. So you'll have like in one direction, you'll have fluxes with some non-zero value going out, and then back in, you'll have a zero value flux. And I think that's very big difference in current, essentially, or that very big current, I think is what causes it. I don't have a good or more formal explanation for it than that.
I mean, it almost seems like you can see like the fuel pins or whatever those like dots are too.
Yeah, so that's the guide tubes where there's also like a lot of thermal flux, not a lot of fast flux, and that's doing something as well.
Just interesting.
It is, yeah, it'd be nice to formalize why that is a little bit more. Yes.
On the perturbation method where you perturb the geometry, some of the pictures you showed, it looked like, will the neutrons still be traveling in straight lines in the perturbed geometry?
That's why you want to use data tracking and not surface tracking.
Right.
Because, not necessarily according to what the deformation is.
So I guess my follow-up question would be, this is a thought experiment with stellarators, right? You've got a donut that's been perturbed into a swirly donut via some sort of mathematical transformation. So in principle, could you track in the original donut and then perturb and then use the geometry perturbation to get the swirly donut?
I need to think about this. I don't know. I don't know the limits of, I think in principle.
Is there restrictions on the kinds of transformations you can do?
Yeah, I mean, there's some restrictions. I don't know about, I mean, like the transformation field, it has to be continuous. It has to, I don't know, like end at zero, like at the end of, like, there are like some restrictions. I don't know about that specifically. I will need to think about that and talk about it with Nikolai because he's the reference of geometries. I'm not sure, but that would be, that sounds cool, honestly. If you could, not sure. That's the honest answer.
Any more?
I have one more just question. Maybe we can talk about it later. But for the zeta method, it's formulated for an input value of K effective. Could you optimize something else, like an R different tally value instead of K effective?
I mean, you could, as you like to target.
Target, yeah, it's a better word,
yeah. I mean,
it seems like K effective is just a global tally, right? So you could focus it around some.
I think so. I mean, like anything that you can, fit in your equation. Say like,
so like if I had a breeder region, it was like I want to hit a TBR of 1.2. Could I modify the outer inner boundary?
Yeah, I think so. Yeah, as long as you can. Yeah.
That could be interesting.
Or like, if you were, I don't know, you give the density of your detector to target a certain leakage.
Right.
Yeah. I think you could do all of that.
Okay.
I haven't tried, but I don't see why not. If convergence allows, but it's just about scaling the right things.
Yeah. Exactly. Okay. Cool. That'll be interesting to talk about. Cool.
Okay, if we just thank our speakers one last time. So thank you all for coming. If anyone would like to talk to our speakers more or share your research with them, they'll be available 2:30 to 3:30 in ERB 402. Probably might be a little late on 2:30.